11.7, we're going to look at power series, and then we're going to look at 2 examples of the power series and a couple of applications in the next section. And so what you want to, this is probably something you've never seen before, and what you want to think of it is just another function, another idea. You know, like the first time you saw 3x squared plus 7x plus 2, it may have freaked you out. But then you learn to deal with it, and now you know how to find zeros and vertex, and you know what the graph looks like, and all of that kind of stuff. So this is sort of your first application of series, and it's this concept of the power series. So that's how you're going to want to approach your understanding of it. Now, if you haven't completed the homework or really looked at the other lectures and you don't feel very good about the different tests, this section is going to be extremely painful. So it's definitely like try to give yourself some at least foundation understanding of the other sections before you try to get this one. This is really an example of building. I did go online and I found a summary of the Convergent test for series, and that's under your Unit 4 folder. And I'll show it to you here, and we'll have that out today so that we can kind of work on it. So let's go ahead and get started. If you look, I have it right here. This was the file that I inserted, and it has the different, it's probably hard to read on the computer. Let's see. The different tests and whether they give you convergence or divergence, and then some good comments on each one of them. So that's nice. It's a nice little sheet, and I will allow you to have this sheet on the final exam. Of course, if you're taking the online exam, I would expect that you'd have it in front of you as a tool. Okay, so looking back now, these are the notes. It says a power series about, okay, so this is a definition. Just take it, all right? Just take it. We're going to define something called a power series. So those are our new words. About x equals 0 is a series of the form c sub n x to the n, and it would be equal to c sub 0, c sub 1 times x, c sub 2 times x squared, plus yada, 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 c sub n x to the n. And c is just a coefficient, like just a constant, just like a number. So this could be 5x to the n, right, or 12x to the n. Or actually, these numbers can change because it's c sub n. They could be different numbers. Now, if you want to have a power series about x equals a, it's going to have this form where it's kind of like you just do x minus a instead of, so you could almost think of this one as where a was 0. So it's kind of where it's centered about. And this is its form, right? So that's just a definition. Just be okay. Just live with the definition for a minute. Okay. So here they say if you wanted to look at a geometric series, what you can do is take all the coefficients to be 1 in the first equation, and you get just, that's how you can get the geometric series. All right, this is the geometric power series. We know what a geometric looks like. We can create the geometric power series by restricting the c sub n's to just be 1. Okay, so now we have the geometric. And then what did we do? This is a power series. It's different than what we've been looking at before, because what we looked at before, we always had numbers, right? But now we have this variable x, right? But when we were looking at the geometric, we could tell whether it converged or diverged. How could we tell if it converged or diverged? We looked at the r, and the absolute value of r had to be between less than 1, or r had to be between -1 and 1, right? So if r was between -1 and 1, we knew it converged. And the way we found r is we divide the next term by the previous term, right? So if you do x squared divided by x, you just get x, right? So in order for this to converge, this x is like my r. So the absolute value of x has to be less than 1. Or x has to be between -1 and 1, right? So this is a geometric series with the first term 1 and a ratio x. remember the formula for the convergence for geometric is A over 1 minus R. So they say it converges to 1 over 1 minus X as long as X is less than, the absolute value of X is less than 1. Okay? And so what that means is that we can write 1 over 1 minus X, because that's what this function is equal to, as the polynomial 1 plus X squared plus yada, 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 X to the n. Okay, that's huge. Just right there, just that's just weird, right? You took a rational expression, 1 over 1 minus X, and you wrote it as a power series or a polynomial. I mean, it's basically a polynomial with infinite terms, right? Okay? All right, as long as the X is between -1 and 1. So what that means is if you were to graph this function, the first function is the function in blue right here. That's your friend 1 over 1 minus X. That's the graph of it right there in blue. And what's so very interesting about this is that the closer X is, the closer you are to 0 for X, you notice that you get right on there. If X were 0, this equation is 1, and this equation is 1. You're right there, right? Now, if you looked at if you sort of decided to, what you're going to do is you're going to use this to, you can use this function to approximate particular values of 1 over 1 minus X. But obviously you'd have to stop. When do you stop, right? Well, it turns out the closer you are to 0, you can stop like after the first term or after the first 2 terms. This is after the first 3 terms. They did 1 plus X squared. Now, if you want to use this polynomial to approximate a value of the function closer to 1, you need to have more terms of the series in order to do that. Okay? So what you can see in your mind, or what you can see to yourself, is that if you look at the graph of 1 plus X squared all the way up to plus X plus 8, it looks pretty close to the graph of 1 over 1 minus X. If you keep going out more terms, it's going to get closer and closer. But it's only going to be a good approximation between -1 and 1. You know what I'm saying? It's going to, because that's when the X is between -1 and 1. So you can use this power series as another way to represent 1 over 1 minus X. Now, you may want to know why you would do that, and we'll talk about that in just a minute. But for right now, all you need to know is, okay, I'm defining this new function called a power series, and if I let the constants equal 1, that's called the geometric power series. And I know about geometrics. I know a geometric will converge when the ratio is 1. So if I let the X be between, the absolute value of X is less than 1, that's going to be your ratio, then I can say exactly what it converges to, 1 over 1 minus 1 over 1 minus X. And so then I can write this function as that, as a power series. It's really kind of cool. Because what's neat about this function, if you were to integrate that, can you think about anything? If you were going to integrate that function, what would it be? Not quite. Not quite that hard. If you wanted to integrate this, what do you think you would get? Integral of 1 over 1 minus X. Mm-hmm. It's going to have a negative in it, but it's going to be, right, because you do the u is 1 minus X, and so du is going to be negative dx. So it's going to be negative ln 1 minus X, right? Well, it turns out that you can integrate each of these. And so you can integrate 1, which would be X, and this would be X squared over 2, and this would be X cubed over 3, right? And then all of a sudden, you now have, if you integrate this, you get negative ln 1 minus X, which you, without a calculator, do not know for different values of X what the answer is. But this, if it's X squared over 2, X cubed over 3, you could actually compute what those numbers are. And so you can approximate natural log using power series. It's pretty cool. Are you there, Brandon, sort of? No? Yes? Yeah. I mean, I've got goosebumps because I finally get it at 38. But you guys are a lot smarter than me. So. All right, so what you're going to want to do is, all right, so you've got these power series. It's this new thing that Mrs. Brooks told us about, and it's just got x's in here. That's how it's different. Before we didn't have x's. All our series had numbers, right? So all we're going to do now is we're going to use all our wonderful skills that we have learned about convergence, how to figure out whether a series converges or diverges, and we're going to say, okay, for what values of x do the following power series converge? So we're going to have to look at this, use one of our tests, and try and figure out what x's will work to make that converge, if we can come up with any. Okay, so let's look at A. This is an alternating series, right? And we've got x minus x squared over 2 plus x cubed over 3 minus yada, yada, yada. Okay. Now, a lot of times, the best test to apply is going to be like either the ratio test, they do the ratio, and they do the root test a lot. And remember, when you're looking at the ratio and the root test, let's go back to them real quickly. If you look at the ratio test, the rule was that your L, so you looked at the next term divided by the previous term, a sub n plus 1 over a sub n, and if it was equal to L, some number, remember if L was less than 1, it would converge, but if L is greater than 1 or infinite, then it diverged, right? And then for the root test, the same, you took the nth root of it, and it had to be less than 1. Okay, so if I come back in here and look at this series, x minus x squared over 2 plus x cubed over 3, what I'm going to do is I'm going to look at u n plus 1, so like x cubed over 3 divided by u n, okay? So what I'm saying there is I'm going to look at x to the n plus 1 over n plus 1 divided by x to the n over n, okay? And since I'm looking at the absolute value, the fact that it alternates, I can just throw that out. I don't have to worry about it. So this is x to the n plus 1 over n plus 1 times n over x to the n, right? And so then this simplifies as n over n plus 1 times, if you have x to the n plus 1 and x to the n, how does that simplify? That's just going to be x. Right, because this is x to the n and this is times x, and you can cancel that x to the n. You with me? Yeah. Okay, and so then that's just x. And we would have absolute value because all along you have to think of the absolute value here. And n, of course, is positive. So. Okay, so as n goes to infinity, though, that's just going to go to the absolute value of x. Because remember, you look at the limit of the next term divided by the previous term. That's what we do with the ratio test. Okay, and what has to be true about this? In order for the series to converge, this limit has to be less than 1. That's what the ratio test tells us. All right, and so the series converges absolutely when the absolute value of x is less than 1. It diverges if it's greater than 1 because the nth term does not converge to 0. Okay, what about at x equals 1? If x were 1, you're going to get, let's see, back up here, the alternating harmonic series, which we know converges. And at x equals negative 1, we get the negative of the harmonic series, because everything's going to be negative, and that diverges. So we're able to argue that this first series that we looked at, this one right here, A, converges between negative 1 and 1, including 1, and diverges everywhere else. So we're able to say that for values of x between negative 1 and 1, we have this series will converge. Okay, well, let's look at B. We're going to do the same thing for B. We're going to do the ratio test again on B. So you're going to put an n plus 1 in here and an n plus 1 in here. So I'll just to show the work on how they got that. Notice on B it's also alternating, but since you're looking at absolute value, it doesn't matter. So that's going to be x to the 2 times n plus 1 minus 1 over 2 times n plus 1 minus 1, and you're going to divide that by x to the 2n minus 1 over 2n minus 1. So this is going to be x to the 2n plus 2 minus 1, so that's going to be plus 1 over 2n plus 2 minus 1, which is plus 1 again, times x to the 2n minus 1, I'm flipping it, and then x to the 2n. Okay? So you'll have x to the 2n times x to the 2n times x to the negative 1. So your x to the 2n's are going to cancel, and you're going to end up with an x squared there. Does everybody see that? Do you see that or no? No?
Sorry, I got a little lost at the beginning.
Okay, you got lost.
Just with the x squared thing, the x something.
Okay, are you okay with what I did at this step right here?
Not really.
Okay.
Sorry.
Yeah, it's all right. I was thinking that maybe I should just write it all out instead of using their notes because I think it would work better. So that's what I'm going to do. Let me just find a spot to write. I think I can grab it right here. Or not. I was trying to think where the break is. Okay. So we'll look at B right in here with my handwriting. And then with theirs. Okay, so the sum as n goes from 1 to infinity of negative 1 to the n minus 1, x to the 2n minus 1 over 2n minus 1.
Your conference is scheduled to end in 2 minutes. So the
pattern would be, if you put 1 in, you're going to get x over just x, right? So it's because it's going to be, if you put 1 in for n, this is going to be 0. So that's just going to be 1. If you put it 1 in here, 2 minus 1 is 1. So that's x over, if you put 1 in here, it's just 1. Okay, if we put 2 in, we're going to get negative 1. So it's 2 minus 1, which will be 1. So this will make it a minus. If I put 2 in here, I'm going to get 2 squared. 2 times 2 is 4 minus 1, so x cubed over 3, right? 2, 4, yeah? If I put 3 in, I'm going to have a positive. Here, this is going to be 2 times 3 is 6, minus 1 is 5. That's x to the 5 over, put a 3 in here, 5, okay? And so you probably will get the pattern, you get the pattern from there on. Yes? Okay, now, to see if this power series converges, so far, all of our series, we never had an x in it. That's what's new in this section. We always had numbers here. When we would look at a few terms, we had numbers. So what we're going to do is we're going to say, okay, what numbers will make this converge? All right, so that's what we're trying to find. We're trying to find values for x, which will make it converge. So the way we're going to do that is we're going to look at the ratio test. And what the ratio test tells you to do is to look at the limit as n goes to infinity of the absolute value of the next term.
Your conference is now over. Goodbye.
Over the previous term, right? And if you get some L, you know that it converges when L is less than 1, and it diverges if L is greater than 1. And you kind of have to look at when L is equal to 1, you kind of have to look at it with different methods. Okay? So what we're going to do is we're going to take this A sub n, and we're going to pop it in here. So we have to look at the next term, which means we're going to put n plus 1 in for n in that. So we're going to look at the limit as n goes to infinity of x to the 2 times n plus 1 minus 1 over 2 times n plus 1. That's a sub n plus 1. Then we're going to divide that by a sub n, which is x to the 2n minus 1 over 2n minus 1.
2 minus 1.
Yes, probably. 2n plus 1 minus 1, right? Okay. Now, so we're going to look at the limit as n goes to infinity. I can clean this up a little bit. I can distribute this 2 through. So I'm going to get x to the 2n plus 2, but then I have minus 1. So that's going to be x to the 2n plus 1. Are you okay? And then again here, 2n plus 2 minus 1 is going to be 2n plus 1. I'm going to divide that by x to the 2n minus 1 over 2n minus 1. Okay? Now I'm going to clean that up by flipping this. So this is the limit as n goes to infinity of x to the 2n plus 1 over 2n plus 1 times, when I flip this, it's going to be 2n minus 1 over x to the 2n minus 1. Okay? Then, what happens? Well, you can think of this as x to the 2n times x. Do you agree with that? Okay, so x to the 2n times x over 2n plus 1 times 2n minus 1 over x, and this one I'm going to think of it as x to the 2n times x to the negative 1. So the x to the 2n's will cancel, and an x to the negative 1 in the bottom is the same as an x up top. So I have 2n minus 1 over 2n plus 1 with an x squared. Okay? And what has to be true for that to be, now when we look at the limit as n goes to infinity, this is just going to be 1, right? So what has to be true is that x squared has to be less than 1. Okay? So this will converge if x squared is less than 1. Okay? Because that when you look at the limit as n goes to infinity, this is just going to be x squared. And so what has to be true is that has to be less than 1. Now, it's going to diverge according to the ratio test when x squared is greater than 1. Now, if you look at it, if x is 1, so I'm going to go to this part here. If when we look at as x equals 1, the series becomes, so we're going to put 1 into this process up here. 1 minus a third plus a fifth minus a seventh, right? It's going to look like that. 1 minus a third plus a fifth minus a seventh. That's an alternating series, and that's going to converge. Okay? It also converges at x equals negative 1 because it's an alternating series that satisfies the conditions. So if we put negative 1 in, we get the same, we get another alternating series. So let's see. The value at x equals negative 1 is negative the value of x equals 1. So what we have here is the interval of convergence for that series is from negative 1 to 1 inclusive. Okay? So in this power series, if x is a number between negative 1 or 1, it's always going to converge. All right? Okay. All right, let's look at C now. C is this one, x to the n over n factorial. So that's a pretty exciting one. The only reason I know it's exciting is because someday, soon perhaps, you're going to learn that that is going to be used to approximate E. Okay, so x to the n over n factorial. Let's look at that one, and let's see if we can do some work to figure out where that converges. See if it'll let me put a break in there. No. Okay. No. Okay. I'll just come over here. All right, so it was x to the n over n factorial. All right, and so what we do is we use the ratio test. So we're going to look at the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial divided by x to the n over n plus 1 factorial, right? So we're going to flip that, and that's going to be,
Isn't it just n factorial?
yeah, just going crazy, aren't I? When you flip it, can you do this in your head? If you flip it, you'll have n factorial and n plus 1 factorial. So remember how those cancel, and you'll just have an n plus 1 in the denominator? And then the x to the n plus 1 and the x to the n, when you flip it, that's just going to be, you're just going to have an x in the numerator. So it's going to be x over n plus 1. That feels good? That's what they got right there. Now, as n goes to infinity, that's going to go to 0, the limit of that. So for any x, remember x is just some number. X can be whatever number you want. As n goes to infinity, that's going to go to 0. So this series converges absolutely for all x. That's going to be very exciting soon. Okay, so this is very cool. All right, and then finally, the last one that they look at was this n factorial over times x to the n. That was, this one is the series n factorial times x to the n. You can probably imagine that that one's going to be like what they have here. Here's what they get: n plus 1 factorial, n factorial. So it's, unless x is 0, that's going to go to infinity as n goes to infinity. See how that cleans up? And so this series diverges for all values of x except x equals 0, which is kind of dumb. Because if x equals 0, then it's not very interesting, is it? The whole thing is just going to be 0. It's just going to be 1 plus 0, 0, 0. So it's kind of dumb. But anyway, that one is not a very useful power series. Okay. So then we get to some theorems that we're going to look at. Let's see if I can get this to come back up. Okay, we have what we call the convergence theorem for power series. So if you have a series that looks like this, for x equals c, as long as c is not equal to 0, then it converges absolutely for all x with such that the absolute value of x is less than c, and the absolute value of c, and the series diverges for x equals d. If it diverges for x equals d, then it diverges for all x greater than d as well. Okay? So that's our convergence theorems for power series. And then it turns out that you can have some other, you can have a corollary here when we deal with a power series that's not centered at 0. So it's x minus a. There's a positive number r such that the series diverges for x's, for x with that distance, x minus a, to be greater than r, but it converges when that distance is less than r. And then you have to look at the endpoints. So all you're doing there is kind of shifting it away from 0 if you want to shift it away from 0. It could be that the series converges for every x, which would mean that r equals infinity, or the series converges at x equals a and diverges everywhere else, which is that r equals 0. Okay, and so your rules on how to test for a power series for convergence, you want to, on the examples that I did, we used the ratio test or the nth root test to find the interval where the series converges absolutely. And they tell you this is some open interval. If the interval of convergence is finite, you look at the endpoints, as we did, and you may have to look at use different tests in order to figure out whether they converge or diverge. And if the interval of absolute convergence is between a minus r and a plus r, the series will diverge whenever x minus a is greater than r. It does not even converge conditionally because the nth term does not approach 0. Okay, so if you've got it in there, then you know that it diverges outside of it. Okay, here's some fun stuff, or some things that you'll start to see why this is interesting. It turns out that if you know that the power series converges, then you can define a function as long as your x is within that interval of convergence to be this power series. And then this function has derivatives of all orders inside the interval of convergence. And so you can take the derivative of the function by just term by term, just the n to the n minus 1. Just each piece takes the derivative. And in the same logic, the second derivative, same kind of thing happens. So each of these derived series converges at every interior point of the interval convergence of the original series. So you'll see why this is cool in just a minute. Remember, we started the lesson with this series 1 over 1 minus x, right? Or we started actually with this series and we showed how it was a geometric series that had as its sum 1 over 1 minus x. So we were able to actually say that 1 over 1 minus x was equal to 1 plus x squared plus x cubed. When did this converge? When did we decide that this converged? Right, as long as the absolute value of x was less than 1. And so this is what it looked like. And then what they want you to do is find the derivative. Well, and so what's exciting is you get some new power series. You already know the derivative of 1 over 1 minus x is just going to be 1 over 1 minus x squared, right? Does that make sense to you? You could use, you can write it as 1 minus x to the negative 1, right? The negative 1 comes in front, 1 minus x, negative 1 minus 1, which is negative 2, times the derivative inside, which is negative 1. So that's why it's positive 1 over 1 minus x squared. And then you can take the derivative of each of these pieces. The derivative of 1 is 0. This will be 1, and then 2x, and then 3x squared, and then 4x cubed. So again, you were able to describe this function, 1 over 1 minus x squared, as a power series. It's kind of interesting. Okay? All right. I don't know. Okay. So now we have, and then second derivative, same thing. This function can be described in a new way. It's kind of exciting. Okay. So the same is true with integration, right? You can do term by term integration. That's what they're saying there. And so this is really exciting because the inverse tangent function, you don't know how to do anything with the inverse tangent unless you have a graphing calculator. Like if you wanted the inverse tangent of a particular value, you have to type it into your graphing calculator to get it. And you don't know what your calculator is doing to figure that out, right? Okay, well, if you're going to do, you can actually create a power series for the inverse tangent of x as long as x is between negative 1 and 1. And what you do is you start by saying, okay, I'm going to call the function x minus x cubed over 3 plus x to the fifth over 5 minus yada. This is that pattern. And we already looked at this one, right? We already looked at that series a few minutes ago. We saw that he was right here, right? We looked at that one. And we knew that he converged between negative 1 and 1 inclusive, all right? So we've already looked at that series. Now, if you differentiate each of the terms, notice you'll get 1, and then x squared, and then x to the fourth, and then x to the sixth. You can kind of see the pattern as you take, this is 1, and the 3 comes in front, and they cancel, so that's minus x squared, and the 5 comes in front, plus x to the fourth, Okay. So they differentiate each piece. Now notice, when you do the differentiation, you lose the endpoints. You may still have to look. Notice it's all only for the interior that you're allowed to do that. And if you look at this series, you can see that it is a geometric series with the ratio negative x squared, right? So that means that you can write it as, remember the sum of a series, of the geometric series, is a over 1 minus r. Here's your a. And your r is negative x squared, so you can write it as 1 over 1 plus x squared. Okay, well, hold on a second. Who is that? Well, if we integrate it, it's the inverse tangent, right? So if I think of this derivative, I get the inverse tangent. If I integrate this 1 over 1 plus x squared, I get the inverse tangent. And so it turns out that the series f of x, x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7 is actually a series that equals the inverse tangent function for x values between -1 and 1. So that means that I can approximate the inverse tangent with a polynomial as long as the inverse tangent of x with a polynomial as long as the x is between -1 and 1. Okay? So that's kind of interesting, right? Now, to me, it's like you're probably going, okay, but how did you know to start with this first series, x minus x cubed over 3 plus x to the fifth over 5? You know, how did you know? Well, yeah, I don't know, because these really smart guys have been working on this stuff for a long time. So, I mean, you're really just going to be processing some really amazing thinking that has been occurring. But they just started to see patterns with these series, and it's pretty fascinating. I mean, you know, then they decide to take the derivative of it, and they're like, hey, wait, that's a geometric and that's the arc tangent. I know that's, if I integrate this, it's the arc inverse tangent. And then you come back up to that. That tells you that this function, if the derivative of this function is the inverse arc tangent, then this function must be the inverse tangent function. The integral of this function's derivative, you know, it's kind of an argument. Okay. All right. Well, the same argument can be made for the series for ln. You can find a series representation for the function ln 1 plus x. And the way you can do that is, you know, and this one kind of makes a little bit more sense because you know that the derivative of ln 1 plus x is 1 over 1 plus x, right? So and you also know, we just learned that 1 over 1 plus t can be written as the alternating geometric series. That was the first thing that we talked about. Well, we got 1 over 1 minus x, but we can get to be the alternating. Well, you can just kind of reason through that it wouldn't be alternating. If you think of it this way, you can get it if you alternate it. You know that converges between -1 and 1. And if you integrate this, you're going to get back to the ln of 1 plus x, which tells you that what you can do is integrate each piece of this. So you get t minus t squared over 2 plus t cubed over 3 minus t to the fourth over 4 from 0 to x. And so then you can see that an approximation to ln of 1 plus x can be found with this power series x minus x squared over 2 plus x cubed over 3, as long as your x is between -1 and 1. Okay? So it's kind of some pretty amazing stuff. We have a multiplication theorem for power series. If you have two power series that converge absolutely, then the product is also going to converge absolutely. That's what they're telling you there. And so this is really small, but in this example, they said they're multiplying the geometric series by itself to get a series representation for 1 over 1 minus x quantity squared. So if you let, you know that this geometric series is equal to 1 over 1 minus x, and then b sub x is that. And so if you multiply corresponding terms, let's see. then by the series multiplication theorem, well, this is kind of tricky. Let's see what they did here. My hand's moving. Sorry. No. Sorry. So what they did is they're doing the first term, the first coefficient times the last one, and those are always going to be just ones because the coefficients are just ones, and you're going to have n plus one of them. So what they're telling you is that you, if you multiply these two series together, you're going to have n plus 1 times x to the n. And so then you could write that as 1 plus 2x plus 3x squared plus 4x cubed. And that would be the series for 1 over 1 minus x squared, and it converges absolutely as long as x is less than 1. Okay. All right. So those are just, really all you're doing in this section is messing around with different, the different power series. So let's look at some more homework problems and see if we can do some of these. Maybe we'll just try some of the online homework. What's the password? Is it cat or frog? Okay, so this is number 1 on the online homework. They want you to consider the series the sum as n goes from 0 to infinity of -1 to the n, 10x plus 3 to the n. And the first question that they ask you is find the series radius and interval of convergence. Find the series radius and interval of convergence. Okay. And so what you might want to do is kind of consider, put out some different, write some terms of it out. Okay, when n is 0, you're just going to get, obviously, 1. When n is 1, it's going to alternate. It's going to start the negative. And that's going to be 10x plus 3. And when n is 2, you'll have a plus, and it'll be 10x plus 3 squared. And when n is 3, then you'll have 10x plus 3 cubed. Oh, but it'll be a minus, yes. And we'll be alternating. Good. Okay, and so then that will be the pattern. So if we were to look at this, we probably should look at the ratio test first. So we're going to use the ratio test. And we're going to look at the limit as n goes to infinity of a sub n plus 1 over a sub n. So in this case, and it's in the absolute value, and so we're not going to worry about the fact that it's alternating. We don't have to worry about that. So that's going to be 10x plus 3 to the n plus 1 over 10x plus 3 to the n, right? And so what do you get when you, and we always have to look at the limit. So we'll look at the limit. Well, this is going to be the limit as n goes to infinity of, this will just be 10x plus 3, right? Okay. And what is that limit going to be? And of course, it's an absolute way. Well, there's no n even in here, so it's just 10x plus 3, right? Absolute value of 10x plus 3. Well, according to the ratio test, this is going to have to be less than 1 in order for it to converge, right? So what we can do is what this means is to sandwich this in between 1 and negative 1, and then solve for x on either side. So you'll subtract 3. So you'll get negative 4 is less than 10x, which is less than negative 2. And then you'll divide both sides by, or everything by 10, and you'll get negative 2/5 is less than x, which is less than negative 1/5. Okay? And that is, that's your kind of your interior convergence interval. But what you need to do is you need to plug in negative 2/5 into the original function and negative 1/5 at different times to see what the convergence would be, if at the endpoints. So if we consider the endpoints, we're going to look our thing. It was the series n goes from 0 to infinity, negative 1 to the n, and then it's going to be 10x. It was going to be negative 2/5 though, plus 3 to the n. So that's going to be the series n goes from 0 to infinity, negative 1 to the n. All right, this is negative 20/5. This is, that would be 15/5, right? Negative 20/5 and then 15/5. So that's going to be negative 5/5, right? Or negative 1 to the n. All right? And that simplifies as the series n goes from 0 to infinity. When the bases are the same, you can add the exponents, so that's going to be negative 1 to the 2n, right? Which is like negative 1 squared to the n, which is the same as 1 to the n. You with me? Positive 1 to the n. Okay, well, what does that do? Remember, what's the whole idea? What are we trying to figure out what this does? What does this look like? Well, this looks like 1 plus 1 plus 1 plus yada, yada, yada. Right? Yes? Okay, and what does that do? Your choice, yeah, it's going to diverge by the nth term test, right? Because you're always adding 1, so it's never going to, it has to, in order for a series to converge, the nth term has to go to 0. So you know that this problem, this at the endpoint, you're not going to include it. You're not going to include negative 2/5. Now we have to do the same thing for the negative 1/5. So we're going to look at the series as n goes from 0 to infinity, negative 1 to the n, and then 10 times negative 1/5 plus 3 to the nth power. Okay, so this is negative 10 fifths. This is 15 fifths. So this is going to be 5 fifths. So that's going to be 1. So this is the series n goes from 0 to infinity of -1 to the n times 1 to the n, right? And that is okay, so that's going to look like what? Well, that's going to look like -1, or let's see, when we put 0 in, we're going to get 1. Erase? It doesn't want to erase. Okay. 1, -1, 1, -1, right? And continue on that pattern. But again, it fails the alternate, it never goes to 0. The nth term does not go to 0. So it diverges. And you could say that it diverges with the alternating series test because it's an alternating series, and the alternating series requires that the nth term go to 0, which it does not. It does not. Right? Okay.
How is it not technically added to 0?
No, because it could be 1. It depends where you stop. So it could be 1. It doesn't. The alternating series test does require that the limit as n goes to infinity of a sub n equals 0, and that does not happen. Does that make sense? You cannot say that. It's either 1 or -1. It's not 0. Okay. All right, and so our the interval of convergence is just going to be from -2/5 to -1/5, not including the endpoints. Okay. Now they want the radius of convergence. And what you do is you need to find half the distance of the interval of convergence. See, what's happening, the radius of convergence was this idea, find the radius of convergence. And see, this one, it's obvious that it's not centered at 0, right? 0 is not even in there. The 4 examples that I look like, they were all kind of, that we looked at earlier, they were centered around 0, but this one's not. And so you want to look at this x minus a is less than r. So you want to figure out what this r is. And it's going to be from where you are at the x, you add the same amount on either side. So we just want to compute half the distance. So find half the distance of the interval of convergence. So you're just going to figure out the length of that interval. So if you do -1/5 minus -2/5 and divide that by 2. So that's going to be 1/5 divided by 2. It's 1/10. So you just find the length of the interval and divide by 2. That gives you the radius. Basically, you want to center this somewhere. Okay? And then it says, the next question that they want to know is, they just want to know for what values of x does the series converge absolutely and versus converging conditionally. But this series is going to converge absolutely. We don't have any conditional convergence here because of the way that it works. So we can say that this converges absolutely. Converges absolutely. In the interval. from negative 2/5 to negative 1/5. Okay, so that was just like one of the homework problems. But let's see, this one, pretty much on the homework, you're going to just be looking for the radius and intervals of convergence. No, I don't think there's too many. Let me see. There are 13 opportunities to find radius of convergence. I'm trying to think. Let me see if there's, yeah, it looks like that's all we're going to do. And so the process is the same for all of these, except let's see. I think I'm going to stop for now. I might do a couple of online. I want you guys to try a few of these, and then I might do a couple of the homework. Like I might do number 12 after you've tried it and kind of got the hang of it. So you're going to look at finding these intervals of convergence. So that stuff that we looked at in the notes about how you get to the logarithm and all of that, those are like consequences of these series, but you don't have to find that. So you're going to know that. Those are known things. Those are almost like proofs that we did. You're not going to have to like come up with that stuff yourself. All you're going to have to come up with is I give you a series and you tell me the interval of convergence and the radius of convergence. Does that make sense? That's all you're going to have to do. You're not going to have to say, oh, wow, look, this is the logarithm, and oh, well, look, this is the exponential. That's all sort of like a consequence that we already know or that we're going to determine. So I don't know. Did it go okay?
Not bad. I just think
Yeah. Brandon, you all right? What do you think?
I'm good.
You're good. You got toilet paper there? Are you all stuffed up?
Yes.
This is a big day. I mean, series, I don't know. It is a big day. I mean, you figured out, go home and tell your mom or your dad or your wife that you know how to compute an approximation to the inverse tangent of x as long as she asks you an x between -1 and 1.
I know exactly what look
Yeah.
you get.
Pardon?
I know exactly what look you get.
I mean, because really, you didn't know how to do that. Now, if you want the inverse tangent of 12, you're still out of luck. But for all the infinitely many numbers between -1 and 1, you are good to go. You can approximate them. That's big news. Right. So thank God for the calculator because, I mean, it's not like it's really that fun either, how you have to compute it. You know, you have to do a lot of polynomial, but this is what these guys were doing years and years and years ago. So it's kind of, that's why, I don't know, you guys may not have ever even seen this, but when I was in school, the back of our book would be about this thick, not just with the answers to the odds, but also with all of these tables. And they would be log tables, or they would be sign tables. They would be tables of values, and then you would someone would have gone through and done the series approximation to a given and those would be the numbers, and so you would have them. But see, your calculator does all that work for you. So, I don't know. It's kind of exciting, maybe. All right. Okay. I guess I'll see you guys later. I was watching I'll tell you this as really did you get the Parade magazine this weekend? On the Sunday paper, they have a Parade magazine, you know. In there, they were talking about highest earn, or just what people earn. That's the title. Every year they do this. And they have pictures of people all around the world, all around the country, and how much they earn. You know, like they even actually have a college professor somewhere, I don't know, they get $26,000 a year. That's what they make. You know, and then they had this, they must not work. They must work part-time or something. But then they had like a janitor that makes like $39,000, and then they have Jay Leno who makes like $65 million or something a year, or maybe not, it's 35. I don't know, it's 32 million or something. I don't know. All these different people. Well, then they have this guy, Mark, and it might not even be Mark Zuckerman, or he's the inventor of Facebook. He's 25 years old, and he's worth $3 billion. $3 billion. So Becky, who's 12, is thinking, well, I'm going to be his friend on Facebook, because she's thinking all I have to do is hook up with this guy and I'll be set. So she types in his name to find out, who he is and all this. And then there's a video. He does have his own Facebook page, but it's more like a fan page. You can just be a fan of him. You can't friend him or whatever. And as you go through, there's a video and it shows the Facebook people working and talking about what they have are these, I've forgotten what they call it. They have these nights where it's like a cram night or something, where they say, okay, for 24 hours, all we're going to do is just come up with crazy coding, or it's like 2 days where the whole focus of the night is just to create. And one night they came up with the whole interface for how you upload videos in Facebook. And what they're saying about Facebook that's better than YouTube is that only people, if you upload a video to Facebook, only your friends see that video, not everyone. As long as you set your security correctly, right? That's what I'm thinking. But anyway, and so one night they coded all of that. And Becky's, of course, she's like, well, it's no big deal. All I do is hit upload. And there, she has no idea how totally amazing it is that whole thing happened.
I hated doing coding when I took computer programming.
Yeah, and
I'll say something.
they just all stay up all night and drink a ton of coffee and just code. But those are mathematicians. Those are the guys then that the guys back in the day would be adding, finding polynomials and figuring out and making all those tables. They probably just stayed up, 3 nights in a row to create this huge table. And then, anytime you wanted to know the log of 6, you didn't have to recreate it. You just looked at the table, So I don't know what I'm talking about. I'm just saying. So all you need to do is figure out you just need one good idea. If you can get it before you're 25, you can be worth $3 billion.